Alright, so here's another easy problem based on SHM. It is a match between two columns, so let's get into it. First of all, we need to just write the corresponding time periods for all these four situations. The first one is a simple pendulum of length 3L oscillating with a small amplitude, in a lift moving down with a retardation of g by 2. So you have a lift, you have a pendulum in it, and the lift itself, the elevator, as you might want to call it, is going down with a retardation of g by 2. Now, when you have something going down with a retardation of g by 2, you might as well consider it to be an acceleration in the upward direction with g by 2. So that means that the g effective in this case, remember whenever you have a situation wherein you have an SHM happening with regards to pendulums, SHM happening within accelerated situations, you try to write the g effective. The g effective in this case is going to be the g that had already been there, and the g by 2 that you introduce by accelerating upwards. Since you're accelerating upwards, you add a positive sign. So this gives you 3g by 2. And the length is 3L, so the time period is going to be 2 pi, and the length is 3L divided by 3g by 2. That gives us 2L by g. So the answer to A part is R. The second one is two springs of force constants K and 2K are connected to a mass as shown below. So these two springs are connected in parallel. If you push one of these springs by a distance x, the other one automatically gets pulled by a distance x. So the effective spring constant in this case, the effective spring constant is equal to 3K. And the mass it is pulling is m. And we know by our experience that the time period for spring mass systems is equal to 2 pi k by m, m by k, and k effective to be more precise. And k effective right here is 3k, so this option right here. So the answer is S to part B. And the third part is a standard question. It says the time period of small oscillation of a uniform rod of length L smoothly hinged at one end. The rod oscillates in a vertical plane. So let's say the situation is something like this. The rod hangs from here, point O. The time period right now is equal to 2 pi, and in the square root you have the moment of inertia. So the moment of inertia about the point O divided by the distance between the hinge and the center of mass times the mass of the rod, and the distance is L by 2, and you have a G right there as well. The moment of inertia about O, we know that is equal to 1 by 3 ml squared. And once you solve this, this is equal to 2 pi 2L by 3G, and that's the option P. Okay, so let me just write that right there, P. The fourth part is, well, you can try to solve it using first principles as well, but since it's a standard problem, we will just read it and just plug it into the formula and get a result. A cubical block of edge 2L and specific density rho by 2 is in equilibrium with some volume inside water. They forgot to write the density of density rho. Filled in a large fixed container, neglect viscous forces and surface tension, that is, everything is ideal. The time period of small oscillations of the block in vertical direction. Well, we can just write the equation for this. The equation for this is 2 pi square root of m over rho times the cross-sectional area multiplied by g. This m right here, you can write this as the density of the block times its volume, so A times 2L. And rho 2's get cancelled out, and you have an L remaining here, and you have a G remaining there. So this time period is equal to 2 pi times root of L by G, which is option Q.